This is a star shroom, and despite its questionable design, it at least looks like it can survive in the vacuum of space. And now this is your spaceship. What? Why? The Super Mario Galaxy universe is filled with lots of wacky physics, to say the very least, and out of all of the inconsistencies in the two games, one has always stuck out to me. How on earth are you breathing? First of all, you might say, well, this is Mario. This is Mario we're talking about. What if he isn't your regular breathing mammal and doesn't in fact need oxygen to survive? Wrong, and here's about 13 reasons why. Talking. This requires air to be pushed through our windpipe, through our respiratory system, through into our larynx, which causes our vocal cords to vibrate, producing a noise almost like a guitar string. Watch. Number 2, basic fucking biology. You see all of this jumping and running that this man does? Well, that requires energy. Allow me to introduce you to aerobic respiration. Our food, which we also don't see Mario eat for some reason. What's up with that? Maybe it's the mushrooms. It's probably the mushrooms. Produces carbon dioxide, water, and energy every time we use one of our muscles. So you tell me how this man is pulling off incredible feats of physical activity without taking a gasp of that sweet, sweet air. And finally, water levels. Literally, there's a breathing meter. He literally perishes if he spends too much time underwater. Who are you arguing against here? What more evidence do you need, dummy? So now we've established the facts, let's try and justify how a short Italian plumber can breathe in the vacuum of space, because how else would I want to spend my Wednesday? First of all, what is this? What is this? Grass on my spaceship? I don't think so. This is empirical evidence that there is indeed oxygen present on this ship. How do you ask? Don't be daft. Mitochondria, the powerhouse of the cell. It turns out biology wasn't completely useless. Respiration in a plant cell occurs primarily in the mitochondria. This is how a plant gets its day-to-day energy to be able to grow. And without oxygen present here, it turns from aerobic into anaerobic, which produces stuff like ethanol and lactate, which can be extremely detrimental to a plant's growth and lead to death. So long story short, green is a big no-no in the vacuum of space, yet here we are. Now, obviously, the vacuum of space, even in this Mario Galaxy little fantasy land, can't just be filled with oxygen, because that would be stupid. Without the presence of an atmosphere and, in turn, a certain amount of gravity, there is nothing stopping oxygen from just dissipating into the void of space, being rendered completely unusable as it's spread too thin. Now, of course, this wouldn't be a problem if the entirety of the universe was just filled with oxygen to begin with. However, this causes its own problems. Temperature being one of the biggest. Extreme hot and cold temperatures will have differing effects on the state that oxygen is found in. Extremely hot, next to a star, for example, would mean it could turn into plasma, and then how are you using that? And then on the other end, in the complete vacuum of space, it would freeze at around negative 218 degrees Celsius, and the baseline heat level of just outer space in general is negative 270, meaning any oxygen that's just floating around will be in solid clump form. How are you breathing in rocks? Doesn't work like that. But now we know there's not just oxygen lingering around in space, we have fundamental proof that there has to be an atmosphere around these ships in order to maintain the life of these plants, and more importantly, Mario's life. But how is it possible? There is absolutely no way that Mario's ship is dense enough to hold that kind of gravitational field. Well, really, there's two options here, and to find them we'll be looking at the different planets or asteroids that we find around the Mario universe. Some of the planets in the Mario universe seem to be completely solid, whereas others seem to be cored by these extremely large black holes. And for simplicity reasons, if you can really even call it that, we're going to start with the solid sphere of mass. There are many different sizes of asteroids and planets that Mario seems to traverse in these games, but they all seem to have the same gravitational field. And we know this since he's seen jumping at the exact same height regardless of what planet or spaceship he's on. This must mean, however, that all of these planets have different densities. Obviously, we know that gravity is equal to Newton's gravity equation, i.e. the mass of these planets stays the same, it's the density that's changing. So let's take the very first planet slash asteroid that we find ourselves on in the very first game and work off of that. Now, I would say it's going to be extremely hard to find the exact dimensions of this planet, so let's just go off this guy's estimate from online, which, by the way, I'm using so many of this guy's calculations. I'll leave a link to it in the description if you're interested. He says that it's about as wide as a Boeing 747 is long, which I'd say is a fantastic starting point. It comes out to about 230 feet. So if we rearrange for mass 2, which is the planet, mass 1 is Mario, which comes out to about 33.3 kilograms. That's just found online though, it could be very wrong. The gravitational force of the Earth on us, because that's what we're basing this off, and of course the radius of a Boeing 747, we get that the mass of this planet is around 1.8 times 10 to the 14 kilograms, which despite the number isn't actually that large. The smallest moons and dwarf planets in our solar system can range up to 2 times 10 to the 20 kilograms, but 2 times 10 to the 14 is just about the mass of Halley's Comet, which we have observed in our universe. Now, the one issue with this, however, is that Halley's Comet is just about 9.3 by 5 miles in size, which is just a smidge too large. This would mean that to achieve the same size as the planet we're trying to find, we would need to increase the density by decreasing the volume, therefore keeping the mass the same as we need it for the gravitational constant to stay true. This is where it gets slightly tricky, however, because if we were to condense Halley's Comet to the size of around a 747, we would get a density of 1 times 10 to the 9 kilograms per meter cubed, which by complete coincidence is almost the exact same density as the crust of a neutron star. These are stars which have ran out of energy, and in doing so, they now don't have the energy to counteract the crushing grip of gravity, causing them to compress into what is known as neutronium. This is fantastic. As we have observed this in the real world, we know it is possible. However, one small problem is that neutronium is extremely radioactive. It is made up completely of neutrons, with no protons or electrons present, which has a half-life of around 10 minutes, which, if you don't know, is how much time it takes for half of a radioactive substance to decay. So not only would Mario get so many forms of cancer, he would also be walking on something that's literally disappearing in front of his eyes. Just a quick side note for the people who didn't ask why this happens in real life, is because the neutronium is just the crust of the stars. The core is what's giving the immense gravitational pressure, which is enough to overcome the weak nuclear force that drives beta decay. Without this strong gravitational core, the entire crust would just disappear within seconds, which would leave Mario not only riddled with cancer, but also floating in the middle of space. But either way, he's riddled with cancer. Maybe Mario is protected from this radiation though by the lumers. I mean, he literally has a star in his hat, which in theory would just be bombarding him with beta radiation anyway, so maybe these magical abilities is what's protecting him. Either way though, we know that the planets in the games don't decay within a couple of hours. This means they must have that strong core we're talking about, which is where we're going to bring in black holes. We can see here that many planets in the Super Mario Galaxy universe are held together by these incredibly large black holes, which, as you probably are already aware, hold the strongest gravitational field in relation to their size in the entire universe. A black hole the size of a grain of sand would still have the mass of a small moon, and therefore the gravitational influence of one, meaning it's definitely strong enough to hold an atmosphere. Now, it's not just gravity that's influential in holding and forming an atmosphere, but we'll get to that at a later point, because firstly, you might be screaming at your screen for the issue that I'm also seeing right now, and if you can't see that, just look at this absolute hunk. That is absolutely massive, especially in relation to how much mass is orbiting it. Now, let me introduce you to the way we're going to find the gravitational power of a black hole, and that is the Schwarzschild equation of gravity. Now, the keen-eyed of you might be saying, well, Lewis, that looks extremely similar to Newton's equation for gravity, and you are absolutely correct. Gold star for you. We have to use this version of the equation, however, as it is ever so slightly different. When Schwarzschild was making his equation for gravity, he was doing it based off Albert Einstein's theory of general relativity, which in other words just accounts for the curvature in space-time that occurs when extreme gravitational forces are in play, like for instance when a black hole is present. If we were to use Newton's equation in this instance, the result would be inaccurate, as it wasn't designed to be used with such extreme forces of gravity that he didn't even know were physically possible at the time of making it. Anyway, we need the mass of of a black hole, and for that we will use the radius, which as we know is about a 1/12 of a Boeing 747. What we're looking for, by the way, here is the Schwarzschild radius, which is the radius of the event horizon of a black hole, in which we will use this formula. Obviously we know that a 1/12 of a Boeing 747 is our Schwarzschild radius for some reason. Also plugging in the speed of light as well as the gravitational constant of the entire universe, and then rearranging for mass, we get this number that I haven't looked at yet. It's quite large. 17,520,598 kilograms. Okay, now plugging this into Schwarzschild's equation for gravity alongside the mass of Mario, 33.3 kilograms, man. He's a small little boy. We get a Newton count on Mario of 1.11 times 10 to the 19 newtons. That will kill him faster than any cancer you could possibly give him. Why on earth is the black hole this big? It is complete and utter overkill. Now, obviously, the gravitational force applied to the orbiting mass is going to be smaller because, well, the orbiting mass has more mass. However, it's still going to be complete and utter annihilation, and all of that mass should just be immediately sucked into the black hole. But there's no explanation for that. Mario's truly broken me. However, if we take these principles and apply them to Mario's spaceship, we might get something that we can work with. Imagine inside of Mario's spaceship, there is a very minuscule, and I mean minuscule, black hole, but it is the perfect size to be able to maintain the same amount of gravity on the surface of the spaceship as it would be on Earth. Now, imagine we have the technology that we don't even know is possible. The technology to encapsulate and contain a black hole is completely out of the realm of our imagination. However, so is having a sentient star under our caps without simultaneously killing us. So let's just presume it exists in this world, shall we? But now we have to worry about so many other things. Earlier on, I spoke about how gravity isn't the only factor in maintaining and forming an atmosphere, so let's get down to business. A magnetic field is extremely important in this process. Without it, any atmosphere would just be ripped away by solar winds and any radiation from nearby stars. Now, that being said, a black hole doesn't naturally have a magnetic field, but what does is the dense plasma in the form of an accretion disk. This theoretically, and this is massively theoretical because obviously we can't prove this, would allow ions and electrons to be manipulated to flow around it, giving it this pseudo-magnetic field, which for our purposes we'll say is completely acceptable. But what about even more radiation, and more specifically, Hawking's radiation? This is a slightly different form of radiation, however, as it is not inherently harmful to humans. However, the threat it does pose is the fact that this black hole will be shrinking. Stephen Hawking says that there are particles and antiparticles that spontaneously appear and annihilate each other all of the time. That's incredibly sus, Stephen. Now, as there's no overall energy change throughout the entire universe, theoretically this can happen. However, when these two particles, one of matter and one of antimatter, appear on the event horizon of a black hole, and one is sucked in, one is left standing and therefore cannot annihilate the other. This leaves an overall energy imbalance on a universal scale, which obviously cannot happen. That is illegal. So therefore, this particle that the black hole has consumed has taken away mass from it instead of adding to it, which also makes it look like this black hole has excreted a particle, which isn't in theory what's actually happening, but it's just so cool, right? It's just so cool. So as we've established, this black hole will be shrinking, as also there is no mass going into this contained black hole that we're talking about. But how long would that take? Well, this equation is nice enough to tell us exactly how long it would take for the black hole to completely evaporate. By the way, let's just go off on a tangent real quick because I can bet most people won't know what that is. This is the Planck constant, which is a fundamental physical constant which sets the scale for the quantization of physical phenomena. Or in other words, it is the smallest amount of energy over the smallest amount of time, making it the building block for energy, if you kind of get what I'm saying there. Now, as you can see, this is denoted by H, but in the equation for Hawking's radiation, there's this weird symbol, which, if you don't know, that is the reduced form of Planck's constant. Why? All this is really doing is making it easier to read the final equation, because otherwise this would just be in place of that and it just makes it messier, and scientists like to be neat and tidy because that is neat and tidy to scientists. So there's your answer. Stop questioning it. So that all being said, the time it would take for our black hole to completely evaporate is around 2.73 times 10 to the 73 seconds. Which you might say, oh, so what's that in years? Well, let me just read this off for you. It's only 93 vigintillion, 548 novemdecillion, 863 octodecillion, 521 septendecillion, 55 sexdecillion, 384 quindecillion years that would take. A constant gas source is also needed to maintain an atmosphere, but as we've already discussed, don't worry guys, we have plants on board and photosynthesis. It produces gas. So possible. I'm so glad we had this nice friendly discussion. I could go into more detail here, but I feel like we've already reached our conclusion. With the correct technology that we don't even know is physically possible, it is possibly, maybe, plausible to make a spaceship that looks like the face of a Nintendo character. How is he breathing in space though? I don't know. I have absolutely no clue. Probably the Magic Star Lady. Thank you and good night.